Uno de los retos que tiene la ciencia de materiales en el futuro es poder explicar y simular qué es lo que está pasando dentro de un material cuando lo sometemos a distintas condiciones, a distintos ensayos, bien sean de tipos mecánicos o de tipo óptico, magnético. Hoy, para hablarnos de cómo hacer esto dentro del campo del comportamiento mecánico, tenemos a HYUNG-JUN. Él está trabajando en la Universidad Politécnica de Madrid, en el Departamento de Ciencia de Materiales, y nos va a hablar acerca de la simulación o métodos de simulación multiescala y sus aplicaciones a distintos campos. Leyó su tesis hace relativamente poco, un poco más de 2 años, en un programa de doble titulación entre la Universidad Nacional de Seúl y el INP de Grenoble, en Francia. Luego ha realizado una estancia postdoctoral entre junio del 2009 y marzo del 2011 en el Centro de Materiales del Ale-Fem, en Francia también, donde ha seguido profundizando en el análisis y la relación entre dinámica de dislocaciones y comportamiento en deformación del material. Y desde hace casi un año es un investigador postdoctoral de la Universidad Politécnica de Madrid a través del programa de excelencia del Campus Internacional de Excelencia Moncloa, de la Complutense, la Universidad Complutense y la Universidad Politécnica de Madrid, una beca Picata que consiguió pues, en una prueba muy competitiva porque hay muchos candidatos, y está pues, continuando con esta línea de trabajo en procesos de simulación de dinámica de dislocaciones y dinámica molecular. De alguna forma sus líneas de investigación se recogen en análisis de experimentos de nanoindentación y dinámica de dislocaciones. Pues para hablarnos de todo esto, le tenemos aquí. Thank you very much for being with us. And, well, it's your turn, it's your time.
Thank you. Thank you for good introduction, and thank you for coming for this early morning. Yeah. I'd like to show you my work I have done regarding the multiscale simulation method and their application. This presentation is including the Ale-Fem method, crystal plasticity method, and distortion dynamics, and the molecular dynamics. First, I'd like to introduce what is the multiscale simulation and its object, and then I'll show you several programs according to its scales, macro scales, and atomic scales. Plastic deformation, including the many mechanisms from the atomic scale, atom-atom relationship, to the macro scale. As you can see, the plastic deformation, including the atom-atom relation, and dissociation interaction, and dissociation interface interaction, and the crystal-crystal interaction. And it also including the global geometry and the contact condition. So the multiscale simulation has some objective, which is the developing the only one code, which including all the mechanisms in one, and simulate all the scale of the programs. However, because the size scale is more about the 10 to 13, 10 to 14, so it's almost impossible. So the next alternative way we can simulate, we have the simulation method which covers each size scales from molecular dynamics to the FEM. And then we can make a bridge between the simulation method, which is what I'm doing, and I want to show you. Fortunately and coincidentally, I have experienced all the simulation methods from my master degree to the now. So I can show you some the simulation method of each scales, and then its application for about the simulation scales. Let's begin with the macro-scale simulation, which is about the FEM method and its applications. Usually, FEM method use the Lagrangian method, which is the meshes confine the material deformation directly. So each element of the meshes is usually simulates the deformation of material at this point. So if the material deformed very severely locally, the meshes deformed very much and it distorted, and then it couldn't have the simulation. On the other hand, with the ALE simulation, it also meshes follows the material behavior, like the Lagrangian method. However, it also have the correction step, which prohibiting the mesh distortion like this. So it can be simulated even the material has locally severely deformed like this, and it gives the result. So I can show you the two kinds of application which are using the ALE simulation, which are the powder compaction of loading and the FSW, friction stirred welding. Both two cases has the very severe deformation, even locally and globally. So it cannot simulate using the usual FEM method. But with ALE, yes, it can simulate. First, I can show you the powder compaction of loading. When the powder is to contact to the roller, and the void inside the particles can be reduced due to the rearrangement. And as soon as the powder density reaches the critical density, then the powders start to deform practically. As soon as it passes through the roller gaps, and it re-expansion a bit due to the elastic deformation. All of this procedure can be simulated by this kind of criteria with the three unknown parameters. The parameters can be obtained from the experimental data, like this. Here's the mesh design for simulate the powder compaction. Although I couldn't tell you the exact quantity due to the confidential, but I can show you the inlet powder inlet length is much higher than the outlet length, which is very severe deformation simulations. But with ALE, we can do a simulation. And to see the roll surface pattern effect, I simulate only focusing on the surface roll gap part. So here's the result of densification during the rolling. At the beginning, it begins with very low density, but during the powder compression, you can see, the powders begin with the very low density, but it's compacted after the low compressions. So here is the major result of this simulation. With the low RPM, low speed of the rolling compression, then you can, all the powders inside the rolling can be compacted nice and smoothly. However, with the higher speed of rolling, only the powders near the rollers is compacted, and it gives the huge residual stresses. So, with the high speed of rolling compression, you will produce the very unstable compacted powder. Now I show you the effect of the roll factor. As you can see, where is the huge compared to the zone and where is not. Yeah, the next example is the FSW, friction stir welding. The friction stir welding is the new type of the welding method using the steering of the material. So it gives the locally very severe deformation near the boundary. So it's also very hard to simulate. But with this, the mesh design and the AI method, we can do FSW simulation. The first feature is the plastic deformed joint cases. As you can see, with the steering of this joint, and then it develops the plastic deformed joint. You may not see the ejector value at the highest of the plastic strain case. It's over the 100 cases, so it's too much severe deformation. And we can see the temperature heat flow during the FSW simulation, FSW experiment. So you see the heating is due to the friction, and then it flows like this. Also, we can follow the material flow during the FSW, and then we also simulate the texture evaluation, and then it is confirmed by the experiment. Now, let's scale down to the microscale simulation, such as nano-indentation. The object of nano-indentation is to get the material properties using the load displacement curve and surface imprint. So this nano-indentation procedure can be simulated by the FEM simulation or crystal plasticity. And this kind of simulation is supporting the experimental result and confirming the experimental test. And I will briefly show you about what is the crystal plasticity. The crystal plasticity explains the plastic deformation is using the estimation of the 3D system inside the crystals. Using this, and it used several equations for the flow law and hardening law and evolution law. And it also needs some the parameter to explain the hardening and dissociation evolution. Using these equations and some the parameters, we can simulate the load displacement curve according to the loading direction and orientation changes. And we do a simulation using the crystal plasticity code with just like the nano-indentation experiment. So we do a nano-indentation test from using the both experimentally and computationally. In the experimental part, we do a conical tip indentation, and then we use the 4 types of the crystal, 4 types of the specimen with the 4 different surface orientation and 2 different initial diffusion density. With the FEM part, we do a ejector quantity as the experimental test, and we simulate. We compare the result for experimental and FEM result. Using this nano-indentation test, we can have the load displacement curve. and the slope of the unloading curve, we can have stiffness data. And we also obtaining the contact surface area using the Ale-Fem test, and using both the load space curve and the area data, we can have the hardness data. We do the same procedure for 5 specimens with 4 different orientation and 2 different initial tissue density. As you can see, the load space curve and all the other quantities is totally depends on the initial tissue density. You can see. And we see with the orientation effect like this. This experimental result can be reproduced by the FEM calculation by only using the different initial tissue density. So we do exactly same simulation, same data as experiment. The next one is the surface imprint using the FM test. In this case, all the surface experiment totally depends on its surface orientation. And this surface imprint also reproduced by the FEM simulation like this. So both the qualitatively and the quantity is also very good measurement as the experiment. For this kind of simulation, we do these hardening parameters. And we do an analytic test using the distribution dynamics too. At the beginning of the distribution dynamics, we don't have the dissociation inside the buffer style. So at the beginning, the simulation result is totally same as the FEM calculation. However, as soon as there is some dissociation inside the buffer style, the dissociation structure and the stress period due to the dissociation is affected to the final result. And this system dissociation stresses also affect to the boundary condition of FM calculation. And what is the dissociation dynamics? There are many ways to simulate the dissociation dynamics, but in my cases, the dissociation lines is discretized by edge and screw dissociations. And each segment can be moved due to the applied stress and internal stresses. And in the dissociation simulation, it also includes the local dissociation interactions, such as the annihilation, recombination, junction, and cross-link. And it also simulates with the dissociation interface interactions using the facet algorithms. And here's the video from the beginning of the indentation to the dissociation, the final depth. But I couldn't show you because there's no flash player. However, dissociation loops is generated by the contact of indenters. And the size of dissociation loops is totally dependent on the surface, contact surface. So with the different indentings, the size of generated loops is increasing. So when the generated dissociation loop is large enough to act as the French resources, and dissociation can be generated both from the neutralization of the indenters of the dissociation and the generation by the French resources. As soon as the dissociation density is too much to neutralize beneath the indenters, in that case, the dissociation generated only by the French resources. The next step is we can focus on only the side effect inside the channel and so on. The side effect is usually explained by the dissociation structure. As soon as the dissociation is concentrated locally due to the inclusion or the boundaries, it makes the huge long-range interaction stress, and we have the side effect. The smaller makes stronger. To make a different analysis between these two results, we need to describe this dissociation structure in mathematical variables, such as Nye tensor or geometrically necessary dissociations. And we need a simulation tool which can reproduce the side effect, such as the dissociation dynamics. So we will use the dissociation dynamics to analyze the side effect. And with same method as dissociation dynamics as I explained. And this is the test condition to see a side effect. The dissociation is evolved at each slip plane inside the isolated crystal. Here we have the two different sizes. One is the size of the channel, which is the width, which represents the material size, and the other is the distance between slip planes, which represents the integer size. The integer size is very important because of two reasons. One is it makes the strain measured directly, and it also affects the long range hindrance like this. And then using this simulation situation, we will have the dissociation structures, work hardening, and GND dispersion. Before showing you dissociation dynamics result, I'd like to introduce you some of the analytical solutions for these systems. At first, the Muller solution gives the analytical solution for this kind of multi-slip the pile-up cases. However, in this case, there is no consideration the interaction between the slips. So, on the other hand, the Christophe Defray suggests some alternative analytic solution, which includes both the pile-up and the one slip planes and the interaction between the slip planes. So I'd like to show you the result of the analytic solutions, and which will conform with the dissociation dynamics and supporting the analysis in the dissociation dynamics result. The dissociation dynamics give the dissociation structures, such as the pile-up structure is increasing due to the strain, and then it also gives the load displacement curves. The load displacement curve totally affected by the integer length side. Decreasing the integer length, it gives the more strain with given the stress field. So using this two raw data, we can have the work hardening from the slope of the load displacement curve and the GND dispersion from the dissociation structures. At first, here is the work hardening result. As you can see, the work hardening is totally depends on the ratio between two length scale, the material scale size and integer size. And there's the two regions. At the first region, both the dissociation dynamics and the Muller solution and the Defray solution give the size effect. The smaller makes the stronger. On the other hand, the regions, both the Defray solution and dissociation dynamics gives the stable hardening, but the Muller solution doesn't give the dissociation dynamics result. The reason is there are two kinds of hardening mechanisms. When the distance between two slip planes is large enough to not to fill each other, and the hardening is only due to the pile-up in one slip planes. On the other hand, the decreasing the length between two slip planes, the interaction between the slip planes is also gives the work hardening. So this is the reason why the Muller solution doesn't give the different dynamics result. The Muller one doesn't consider in the interaction between two layers. And we can show you the GND distribution inside the crystal. Here also totally depends on the ratio between two length scales. When the ratio is smaller than 1, here is it is the side effect zone, right, at this case. In this case, the GND density is minimum at the center and the maximum at the boundary, and it increases gradually. However, when the ratio is very big, as the non-side effect zone, in this case, the distribution only accumulated at the boundary, not in the bulk crystal. You can explain this result using the only one assumption. Distribution pile up only when the slip planes at the boundary is filled with the distribution. The reason is the distribution to make a pile up is always need higher energy than the distribution to fill the empty spaces. In this case, when the ratio is very small, it means that there's a few sites at the boundary. So distribution is easy to fill all the sites at the boundary and start to make a pile up from the beginning. On the other hand, when the ratio is very big, it means that there are infinite space at the boundaries. So distribution always fill the empty space, not to make a pile up. The last one, I'd like to show you what I'm doing now, which is the atomic scale, and this is about body growth. The body growth is very important because of it affects to the total pressure, like body growth and coalescence of void. And also around the voids there is the specific plastic flow, and it gives the size effect due to the size of void and so on. So we do a simulation using the micro dynamics and distribution dynamics, and to see a size effect of the void and plastic flow around the voids like this. We do the molecular dynamics, and we focus on the two-dimensional systems. And we introduce some adjusted fluid potential with the hexagonalities. And this molecular dynamics may generate automatically to a dissociation like this. And to generate and the movement of dissociation makes the plastic formation. And here is the system of what we are doing with the molecular dynamics. And we have the crystal, which has several sizes, and the voids. And the void size is controlled by the Fourier impressions. Using this simulation, we check the size effect of the void growth and the dissociation evolution around the voids. Here's the one result, the dissociation evolution is the threshold. As you can see, the dissociation generated at the surface of void and evolved like this. And the voids are crossing by the dissociation and the rest field. And we take the void rows. And as you can see, usually the molecular dynamics gives the no size effect, except for the very few size of the void cases. When the void radius is lesser than the 10 nanometers, and it gives a size effect, but it's reversed one. The smallest void means the faster void loss. It means that it's much lesser hardening kind of thing. The reason is the surface energies. As you can see, the surface energy is very low at the smaller void, and it increases very fast. As soon as the void has the more than 100 angstrom, and it keeps constant with the radius, void radius. The smaller surface energy means that when the void is increasing, it needs the much smaller surface energy to make the increased surface. So it helps to faster void loss. The lower surface energies helps to faster surface void loss. And I usually show you the result of this morning. Here is the result of this morning. And I do the same procedure with the void loss, like the molecular dynamics, and using the diffusion dynamics. And this gives the stressing curves and the void loss, just like the molecular dynamics. And then we can see the void loss system. And for the future work, I do the same procedure with a different size, like the molecular dynamics, and then we can plot in the void loss with the sizes, and then compare it with the molecular dynamics, and experiment like this. For the conclusion, we have the main kind of simulation method, which covered each problem scales. And each simulation method has their own strong point, such as the FM is good for the engineering scale program, and the molecular dynamics and diffusion dynamics is good for scientific programs, such as size effect. So we can, although the multi-scale simulation is not enough to cover all the scale of programs, but we can choose the one of the simulation method according to the problem size. Yeah, thank you for your attention.
Thank you very much for this night talk. We have time for some questions. Please use the microphone.
I have a curiosity about the crystal plasticity modeling when you use the model as function of the dislocation densities. If you can just take 1 minute to explain me the law. On Cp-Fem,
No,
yeah, exactly that
flow
one.
is the same as the usual crystal plastic code. So there is and the hardening law is the same. I think so. The residual strip system comes from the elastic case field, and only the difference is the critical residual shear stress comes from the diffusion density and the interaction of the three systems. And the diffusion density evolved by this Cox-Max evolution laws.
There is one density of dislocation for each of the 12 systems?
Yes.
Different variable?
Yeah.
And you consider only one density independent of their edge or screw dislocations? You have a unique density?
Unique density. There's no consideration between edge and screws.
Okay.
More questions? Okay, thank you very much.